So let me remind you where we were last time, at the end of the last time. So we were looking at the partition function, or in general the generating function of the interacting dimer model. So we have dependence on the box, on the interacting parameter, and in case of the generating function, also a dependence on a set of real variables. So A is a vector, is a set of real variables AE for each edge, well, E running on the edges of the graph. Okay, and it was just, well, this is just e to the w. When you set all the a's to 0, you just get a partition function. And in general, so the generating function would be sum over configurations of the initial weight, so the product of the edges of the weight of the edge, then times the interaction, like the sum over plaquettes of the indicators that you have two parallel dimers, and then plus the sum over all edges of this source variable times the indicator there is a dimer at E. Okay, and then by taking derivatives with respect to the various a's of W, you get all possible multi-dimer correlations. So the thing I did at the end was to something we did was to I gave a representation of the fermionic, so the Grassmann representation for the generating function in the case of no interaction. So this is, let me repeat this, Grassmann representation. Without interaction, so what we saw is that e to the w lambda, so now there is a box but there is no interaction. Lambda equals 0, and then a was given as a Grassmann integral of e to the something I call the action SA of psi, and SA was just psi is just a sum, maybe minus a sum over all edges of, well, we got E times e to the n of E, and EE, if E is an edge with left endpoint of coordinate x and right endpoint of coordinate y, was just psi plus x, psi minus y, times the entry of the Castellan matrix corresponding to the edge. So data may be denoted by k of E. Okay, so this was just I minus 1. Alright, so it's quadratic in the field. Now the point was to prove that you have a similar representation for the generating function with interaction, except that now the action will not be quadratic anymore. So let me repeat the statement of the proposition, and I'll give the proposition in the particular case where the interaction is of the form you sum over all even faces. Let me remind you that we have the Z2 lattice, and we are deciding that one of the two sublattices will be called the even sublattice, and the other one is the odd. It doesn't matter really which one. It's one of them. So we have a sum over these even faces of the indicator that you have either that you have two parallel dimers around this face. So looking at this particular interaction, which is somewhat a simpler form for this proposition, then the statement is that e to the w lambda a is given by an integral deep psi. There is the unperturbed field. And then there is a sum, there is alpha. Alpha is essentially lambda. Alpha is e to the lambda minus 1. Alpha sum over all possible pairs of edges, of parallel edges surrounding an even face. So it would be these two edges, these two, etc. What you have is just product of the two edges in gamma of e gamma times e to the lambda, e to the a. Sorry, again. Yes, e to the a. So you have a sum of products of 4 fields, because now each e contains 2 fields, so you have C. So it's quartic. Yes. All right. So this was a statement. Any questions on this? As I mentioned, for modular interactions, you will get also terms of 6/6, 8, and so on, but smaller and smaller because you will get a parameter in front that will, the interaction parameter in front will be alpha to a higher power. And also, if these objects become large, the prefactor will decay also exponentially with the size of this. But anyway, so let's just look at this particular example. Okay, so let me give the proof. Okay, so let's do the proof, and just for simplicity of notation, let's set all a's to be 0. Just for simplicity. All right, so the starting point is just to take the definition, of course, and so I take a to 0, so I'm just looking at the partition function. So this is just the sum over all configurations. Well, you have in the case where all t's are 1, this is just 1, but then we call it W of m, just maybe not W, it's not W. P of m, P of m, but it could be 1, it will not play no role. Okay, and then you have a product over all even faces of what? Of 1 plus alpha indicator that you have this configuration at F, 1 plus alpha indicator that you have this configuration. And just because the exponent of the, I mean, in the, where is this? In the, each of the interaction term is an indicator, so e to the, that one is either 1 or e to the lambda, so I'm just, if alpha equals this is a negative. Very well, so this is also the product over all gammas of the form as above of 1 plus alpha, well, the indicator of the, if gamma is of the type E, a pair of parallel edges E prime, it's 1 plus alpha, indicator of E, indicator of E prime. Okay, so up to now I haven't done anything. And then the next thing is just to expand this product. So you expand this product, you will take either ones or these indicators. And you count how many times you don't take 1. Okay, so then this is just right, so then you get just sum over m, p of n. Then you get a sum over n larger or equal than 0. If n is 0, it just means I'm taking all ones, otherwise I'm taking a bit of these indicators. And then you have a sum over gamma 1, gamma n, all these possible pairs which are different from one from the other. And then I have for each one of them, I have xc of gamma 1, xc of gamma n, where xc of gamma is just alpha times the product of the two indicators. All right. So then the point is that now what you have, if you divide it by the partition function of the non-interacting model, then if you take the sums out, you have just expectation of a certain number of, well, probability of having a certain number of edges. All right? Now remark that these edges, well, Okay, the edges appearing in all the gammas are distinct because I'm summing. Well, this is where I'm using that I'm summing just on even fields. So I might have these two edges and these two, but I don't have these two because this would belong to an odd face. So the various gammas don't share an edge. They might share a vertex. So you might have a gamma, this one and this one, but this is no problem. Just these two indicators will give zero because you cannot have at the same time dimers here and dimers here. But it's no problem. The expression is still true. Just in this case, we get the zero. Okay. So the point is that all these terms are of the type sum over n of p of m times a certain number of product of indicator like E1 up to E1 of indicator of E1, indicator of E2n, something like this. Well, this of course can be obtained from the generating function of the non-interacting model just by differentiating with respect to alphas and setting so a's and setting a to 0. So each one of these things is just d a e1, d a en of e to the w lambda without interaction, computed at a equals 0. But for this we have an expression. It's there. No, sorry. This is this is with interaction. But okay. But for this, for this we have already the expression, which is this one without the interaction term. Okay. And then from that expression we just take derivatives, and what we see from the expression from the Gaussian representation for e to the non-interacting generating function, we get that this is nothing but an integral lib psi e to the action where I put a to 0, because at the end I put a to 0. And then I have what I have is just a product e1 en, and I have a minus 1 to the power k because there was a to the power n, thanks, because there was a okay, so here there is a 2n, of course, so everything is 2n.
Minus 2n doesn't look interesting.
No, it doesn't look. I mean, it would. I could have even, odd number of things, but not in this expression here. So here, in fact, the sign disappears. Okay. So this is just. I hope this thing is clear. It's just obtained from the expression I gave for the generating function of the non-interacting model. You differentiate with respect to all the a's you have. You get this. Okay. So now you have just to resum, to put this thing in the sum, and well, you will obtain the formula. You just recognize that this is also the expansion of what is up there. I've forgotten anything. Yeah, I think I forgot. No, the alphas are inside here. Okay. Is this step clear from here to what I wanted, or should I? Yeah, so I want to get that one without the a's, because I've set all the a's to 0 for simplicity.
And the k's work out. I'm a little confused whether the k matrices work out.
What is
suppose they do the k?
K, the
Castellane matrix, mate. But maybe
it's included in E. E is psi times the Castellane matrix.
Oh, yes.
And so when you differentiate, you get all these things, and in fact they are there.
Yeah. I think it's okay.
Is it okay for
Yeah.
Well, you just expand that and you get.
Okay, just a I mean, the expansion is really trivial because since this E is a product of Grassmann variables, e to the alpha E is just 1 plus alpha E.
Yes.
So this is,
Sure.
I don't know.
That's totally clear.
Okay.
I'm a little confused, but if the t's are not all equal to 1, the things are, then maybe the left-hand side needs to be modified or what?
So if the t's are not all ones,
Yeah.
then in the e's you have also the t's. So the
Sure. But on the left-hand side there are no t's, but maybe there would be.
Okay, let me see for a second. Which left-hand side? You mean this one?
Yeah.
Here.
On the
Okay,
right-hand
let
side
me
there
see,
will be
let me
t's,
see.
but I don't insist, it's probably okay.
So there's a bunch of T's in the P of M.
So no, here there are t's. No, I think this is. Suppose I divide by z, no?
I mean, the T are Sadikathle matrix.
Yes. So, but the question was, so on the. Suppose I have just one edge. I mean, this counts all the configuration which with that edge, so that gets sort of a T automatically from the indicator. So, sorry. I don't know how.
Well,
I think the formula is correct. I mean, this is T times. It seems correct to me, but if you find a specific point where it looks incorrect, then
No, I just cannot do it in my head to see that it works out. But it looks, generally speaking, it looks good.
Let me try to add the I don't know if it's helpful. So again, the t's are inside the measure P of M. So as Fabio was saying, say you have just one, you are forcing one dimer to appear, and this can also be thought of as t times the derivative with respect to t. The t of that dimer. No, okay. Maybe this is not.
That's
This is
what
not
the
that.
A is doing.
Hmm?
I thought that's what the A is doing when you differentiate.
Yeah, exactly.
Yeah, but the problem is that you have just 3 types of T. So I cannot differentiate independently two dimer things. If I allow all T's to be different, then it plays the same role as the A's.
I see.
It's just that if you want a fix to A, T to 1, or just to have to be periodic, then you better have independent variables which are the A's, or according to which you can differentiate them. Or otherwise, one can take all these to be 1 and then keep the A's, which in particular you can set to be T. Okay, so right. So the outcome is that we wrote down the generating function, partition function as a non.
Sorry, can you comment why is K up here?
So
I mean, I'm not worried by the T because I don't see them here. So I think that they don't play a role, but the K at
So we started from Z. We started from this. I told you accept that this is true.
Yeah.
And then I also told you a determinant of any matrix can be written as. Okay, so up to here.
Yeah.
And then what I'm saying is, if if all CTs are 1, but all T's which were 1, I replace them by e to the AA. then I just modify the Castellan matrix.
Yeah.
So this means that each k of e gets replaced by k of e times a to the ae. And then the thing I obtained was what I call s of c. So the k's are still there, but in addition there are also the a's. Now, now every time I differentiate with respect to an a, I have a psi psi and the corresponding k that goes down.
Sure. Okay. Yeah, I was puzzled because I was thinking that edge correlation were related to k minus 1, so I would expect a k minus 1.
It's
I mean,
Yeah, no, the point is that, yeah, it is, but the point is that when you get things like this, so now suppose you, suppose I want edge correlations, so I have this formula, so for instance, for the non-interactive measure, the probability to have, so at lambda equals 0, to have E1 up to En, you look at there, it's e to the s of c, and then you have E1, En, suppose n is even, so there is no minus 1 to the blah blah. And now each one of them is a product of c plus, c minus, etc. Now you want to apply the big rule, so to contract, every time you get a k minus 1. So from here you can. Any other questions? All right. So the point is to do something with this representation, of course. So what I hope to explain today is. Well, okay. So where did we arrive? We arrived at an expression like deep C e to the sort of quadratic bar, Gaussian bar, plus non-Gaussian. So the first thing you might try to do is to expand in series this thing in terms of powers of alpha and see what happens. So the point will be to convince you, but this is something very well known, that there are, if you do like that, problems appear immediately. Certain terms of the expansion seem divergent because the matrix k minus 1 decays slowly. And then the point that then later Alessandro will develop is how to cure these divergences of the expansion, the final diagrams. Okay, but this is the sort of the starting point. Okay, so before doing that, let me comment on how to decompose. We have this now. We have these Grassmann variables indexed by plus and minus, where plus refers to black vertices and minus to white vertices. But it will actually be convenient to split, so somehow to split every Grassmann variable, be it plus or minus, whatever, into a sum of two things, which are called quasi-particle fields. Okay. I will write something more precise than this later, in a second. So let's say quasi-particle field. So the idea is that, all right, what I call the propagator, the g of xy, which is also in the notation last time probably. I always get confused by who is on the left and who is on the right. Who is right? Is this the usual notation or the? Anyway, so this was just, I write as an integral. If your infinite volume is a sum, but dt to pi square e to the minus ip x minus y mu of p. So as we already saw, mu has two zeros, so there are two singularities in this integral. So what is convenient to do is to rewrite one as the sum of two functions. So here you have times one, but one you write as sort of the sum of two smoothed out indicator function of two sets close to the two singularities. So we want to write one as key, how do I write it? Key plus and key minus. So key plus and key minus are just two functions between 0 and 1, which are concentrated close to this is closed, kind of concentrated near the first singularity, which is t plus, which is also 0, 0. So here I'm taking, sorry, from now on I'm taking all weights to be 1, so that the singularities are in 0, 0 and t. Okay, and then the other one is concentrated near 5 pi. I choose them so that they sum to 1, like the first one is 1 at 0, 0, and it's 0 at the other singularity, and so on. So I hope you see. So it's something like this one, and this one that sum to 1. Okay, so I'm just splitting the integral in where it is close to one singularity or the other, and I do so with smooth functions to avoid bad things. To avoid if I really put some I will just cut the integral, then you will have some oscillation problems from the. But morally, I'm just separating the integral between the part near 0 and the part near pi.
Is that right? That the pole at 0 is the odd or even sublattice, and the other one is.
What do you mean exactly? I mean, x and so
on the left side.
X
well,
and Y can be, so they're both on.
no, sorry. No, x refers to the white side, so it's on the white sublattice, and this one is on the black one.
Yes.
But the two singularities.
I mean, it's maybe a little unfortunate that there are too many pluses and minuses, which might get us confused.
I mean, well, yeah. But they're sort of well, not really. Okay.
It's not so serious.
So in the end, you will have fields with an index above, which refers to black, so to white or black or white, and there's an index below, the omega being also being one of plus or minus, but it could be 1 and 2, referring to one of the two singularities of the thing. It has this field has a position and then two indices, both in minus plus 1. It's just a choice we made.
Can you recall to us why the plus correlation does not stay in Europe? It seems.
Look at the action.
No, the action has in the action you have plus and minus, so when you contract plus plus you get 0, and minus minus you get. So there's a conservation of this index. Okay, maybe I hope I'm not losing it. So just to make sure. So this is this integral, and I'm just splitting it, the contribution of the integral as from the region close to the one singularity and the other. So by definition, this I will call the first one I will call g plus of xy, and the second one, well, I don't quite call it g minus. I extract an oscillating prefactor. So this part of the integral with the chi plus I call g plus. Okay, and the other one I call it g minus times this thing here. The reason is that if you look at what is how do these two things behave, how do the two parts of the integral behave at infinity? The first one. So if you do so, this is just a definition if you want. Then g omega of xy behaves for x minus y equal to infinity as 1 over here phi omega of x minus y, and phi omega, let me remind you that phi omega of x is omega times I wrote it very well. Phi plus is minus I plus 1 x1 plus I plus 1 x2, and phi minus is just minus phi plus complex conjugate. Okay, so the point to retain is that once in the second one I extract this oscillating prefactor, which is just minus 1 to the sum over all the coordinates, then these two things decay as 1 over distance without any oscillations. So this is the whole point of extracting this prefactor. Otherwise, so while the whole G does not decay as 1 over distance because of the oscillations, the splitting is done so that each of the two terms has really a 1 over distance decay. Okay, so this sort of, which is nice because you may want to say that if I take successive derivatives of G, I get faster and faster decay, which is false if you keep the oscillation, because when the derivative falls on the oscillatory part, you don't gain anything. So it is commented for the experts.
So you're gonna have four fields at each
Yeah,
side.
exactly. Okay, so for the moment I've just split the propagator, but what I've just done a manipulation on this function G, but what it corresponds to in terms of fields is that I'm simply what I've done simply is that in terms of fields, what I've done I'm defining C, which is either plus or minus of x, as C plus or minus of x, comma, plus, plus minus 1 to the x. When I write minus 1 to the x is a two-dimensional vector, I mean x1 plus x2, times C plus minus x, comma, minus. Okay, so this is what if you want a definition. I'm splitting the field into the sum of two things. And I'm using the so-called addition principle for Gaussian integration. That means that addition principle means the following. That if you have a matrix G of xy, and you define your Gaussian integration PG so that PG of the product of C satisfies the V rule with propagator G, okay. And if I write the G is a matrix. G has a sum of two matrices, G1 plus G2. Okay. And if I write also that every psi is decomposed as psi, let's say 1 plus psi2 means coordinate by coordinate. If I have an index n, then this is index by index. With the new fields being diagonal in the index 1 with C1, C2 equals 0, and the C1, okay, so it's better if I say it in words. So I'm saying that the two fields, whenever they appear in a contraction, they give 0, they are diagonal in the. And the new field C1 has this propagator G1 and C2 has propagator G2. Okay, so what I'm doing is just a definition. I'm splitting the propagator into two parts, and I'm saying I'm splitting the field in two parts which are diagonal, and for each the good propagator. Then every function of psi I can write it as EG2 EG1 of f of psi 1 plus psi. So it's just a kind of trivial idea. It's like when you have a Gaussian, if you are a probabilist, so if you have a Gaussian family with the covariance matrix sigma, and I write this covariance matrix sigma as the sum of two covariant matrices, both positive, definite, and so on, I can write in distribution the Gaussian family as a sum of two independent Gaussian family, each with its part of covariance. And it's exactly the same thing, and well, the proof is essentially topology.
What does that mean that EG of psi satisfies the weak rule with G?
So what I'm saying here is that if you have any, say, polynomial of psi, and on the left-hand side, what you would have to do is to have this polynomial, and then you choose all possible contractions with this propagator G. On the right-hand side, what you do is you take the same function, but each time you have psi, you write it as psi 1 plus psi 2. You expand all the products, and then you take the expectations or the big rule by considering the phi2 as constants, and you apply, you just contract the psi ones with the now but previous propagator G1. Then what is left, you see it as a function of psi 2, and you apply the big hole with the new propagator G2, then you get the same thing. But it's more complicated to say than to see. It's just, okay. So if you do examples, so for instance, if psi is just if f is a single, then it would be zero. But if you take the function to be just a product of two, and you do it, you see that it's just.
Yeah, that's probably a good way to even make the proof work. If you verify this identity for psi 1.
So exercise. Verify with f of psi being the product of two of them. Let's say in our context
Plus
it
and
is
the minus.
plus x and psi minus y. Verify that this is so. But if you're not too used, it's like decomposing a Gaussian vector into sum of two independent Gaussian vectors. Sorry.
You have to put that the two anti-commute.
The two anti-commute, yes. So you have altogether you have a new family of Gaussian variables. You have now twice as many as before. The anti-commutation rule that stays, but and the new propagator is diagonal in this new index. But everything will anti-commute with everyone else. I can spend if it's not clear, I can spend more time.
Let's move on.
Very well. So now,
Be happy to hang around afterwards to explain it.
okay. So whoever will happy to explain more. Where am I? All right. So let's sort of summarize where we are. Summary until now, and now, as I promised, I will behave as sort of doing things naively and see where problems arise, and then so what did we get? So we want to compute. Suppose we just want to compute the partition function instead of the generating function. Now we have an expression like this: big psi e to the s psi, which is quadratic plus alpha. Did I give it a name? Maybe not. Let me give it a name now. V of psi was just a sum over all gammas of gamma E1, E2. And I think that was it. So quadratic plus quartic, or maybe more. Okay, and then we have also, so psi is symbolic for the collection of all psi plus and all psi minus x in lambda. And also we have decomposed each of them. Once we decompose like that, so V can be also seen as a psi, sorry, it's also the collection of all psi plus minus x omega with x in lambda, in gamma, in lambda, and omega in plus minus. Okay, so it's a function of these L squared times 4 fields. Now, what you could hope is to, let's see what happens expanding. Well, in general, it's not good to expand the partition function, but rather the log of the partition function. So you might, well, alpha is essentially lambda. You might do a Taylor expansion. For the moment, let's not worry whether things would converge or not. So let me write down this expression. So log z is you write down and then comment. Waiting for it to be true, I need to normalize by, let's write it and see if it's true. this means. So what I'm doing is simply the following, like for a probability measure, yeah, it's just a cumulant expansion of it. So for a usual random variable, you would define the nth cumulant, I don't know, what's the standard notation? It's like this. The nth cumulant would be the nth derivative of the Laplace transform computed at lambda equals 0. Just confused about the factorials.
With an n instead of 2.
With an n instead of 2, of course. So and similarly, what is the nth cumulant of this Grassmann polynomial there? What I mean there is just, well, it's just the same thing. It's just the nth derivative with respect to lambda of. Well, maybe not this is so terrible because I want to put it to 0. Okay. So the point is that E0 means just the Grassmann Gaussian representation with respect to the action S0. Okay. So the point is that, so here it's like the expectation of a product of V's, but there are this semicolon, and the effect, which again an algebraic effect, is that when you want to compute, if you want to compute just the expectation of a product of V's, then you know how to do by big rule. So each of them is a product of 4 variables. So you have 4n of them. You have to choose all possible contractions and put the right signature and so on. When you have this semicolon, what happens is that not all contractions are allowed. So this is something that can be proven, I think, inductively on n. So suppose I represent with a block each V. So each V has four fields, but there could be more in complicated movement. And for instance, here n is 4. So when you compute the fourth cumulant of this V, what it means is that you are not allowed to take all possible contractions of the field, but only those such that all the 4 blobs, well, the 4 blobs are connected together. So for instance, this one is allowed, and then all the others you can connect however you want by respecting the. But it's important that there exist at least these lines that connect the 4 fields. Okay, so for instance, this one would not be allowed. So if you want, I'm formulating a proposition. When you have the log of the expectation with respect to the of a quadratic part plus non-quadratic, you can expand. You can expand it as in this cumulant. So there is this cumulant expansion, and each term has this property that it is obtained by all possible contractions except those who would not connect all the polynomials. Okay, is it
Right, so that's if you expanded the Z, you would get the sum over all the graphs, and if you expand the log of Z, you get only the connected graphs, which is a miracle, but
well, it's like it's exactly like expanding the moment generating functions.
it's just one of those wonderful miracles that one has to prove.
If you have not seen it, so it's not trivial. I mean, it requires a proof, but.
Sorry. I mean, your formula for the formula you wrote there for the nth cumulant of the V.
Yes.
Correct? There is no log.
A or U. Yes, of course. Thanks.
Okay.
Yes. Yeah, thanks.
Sorry, another comment. You're missing the n equals 0 term, which is the non-interacting partition function.
That's why I was wondering whether maybe I
Yeah, because you have to divide and multiply by the Gaussian part.
So if I divide here, then it's correct without the one, without the zero.
Yes.
Okay, yeah.
Divide and multiply, there is the...
Okay, yeah, sorry.
No, but then you have to divide also on the left.
Ah, okay.
No.
No, sorry, I didn't understand the comment.
You should write an extra term. Either you write on the left log of z divided by zeta 0, or you add on the right log of zeta 0.
Okay, so this was saying that they would divide.
Yeah, if you do that, you write also on the left z divided by zeta 0.
Yeah, thanks.
Right.
So in fact, yeah, this way, if I set alpha to 0, I get 0 as I should.
Yes.
Okay, so you have this expansion. Sorry, this is kind of messy. You might wonder, well, am I allowed to expand or not? Well, to be conservative, let's say the following. As long, so remark, as long as the volume is finite, you have just a finite number of Gaussian variables, and then this integral, however complicated it is a polynomial in alpha, okay? Because when you expand, as we saw, when you expand this at some point, fields will start repeating, and then all the terms will be 0 up to some point on. So it's a polynomial in alpha, which at alpha equals 0, if I had divided by the normalization, would be 1. So as long as the volume is finite, you have a polynomial which is 1 at 0, at alpha equals 0. So it has certainly no zeros in a small neighborhood of 0. So the log of it is an analytic function, so I'm allowed to expand, at least extremely close to alpha equals 0. So it's a polynomial. And then expansion allowed at least for alpha extremely small. The point is that extremely small can be small with lambda, which we don't want.
What do you mean extremely small? I mean any lambda?
No, but I'm expanding the log.
You want to know there's no zeros here.
Hmm?
You want to know that Z has no zeros
Yeah.
in the origin.
Okay.
No, of course the z can be expanded, no problem, but with log z, it's not analytic everywhere.
Yeah, but I mean, you can take the exponential, then it should be a combinatorial.
Okay, no, but I just wanted to point out that for the moment, let's not worry of the
Yeah,
convergence. This was the only point of this remark. This will
No,
solve
but
it.
it's a combinatorial statement. It's not about analytic function. No, if you, I can take the exponential. No. For,
Well, I mean, suppose you were taking log of 1 plus x.
no, I want to read as an exponential. No, you can write that z equal the exponential of this series,
Which will be a polynomial.
which will be a polynomial.
That's right.
But if the polynomial has zeros and you take the log, you will have a singularity.
No, I understand if I take a log, I have the singularity. So
Yeah.
my problem is if I don't write the log, is correct or not?
Yes.
You can expand all of it.
Then it is true for all alpha.
The log is the problem.
Yes.
So again, sorry.
Yeah. I mean, yours is a combinatorial statement, it's not an analytic statement. No, about disconnected and disconnected.
Log. The above is combinatorial, but the low one is not combinatorial.
Yeah, but if you expand out if you just extract the Grassmann terms in this thing here, you just get a polynomial.
So you can work with formal power series and then everything is fine.
Yes.
I just wanted to point out that, for sure, in any case, for sure, for alpha small enough, there is even it's not just a formal power series. Then you can discuss alpha large, but because my point, actually, the only reason I made this remark is that to say, okay, even assuming you don't have problems of convergence of the series, so I mean, even if you can write down the series, then the problem is that term by term the series can be bad. The terms of the series can look like infinity. Okay, so this is what. So remark is that even single terms can give problem, at least as the volume becomes infinite, as number goes to infinity. Even forgetting the problem of the convergence of the whole series, even term by term, the thing can look problematic. So suppose I'm looking, so let me make an example. Suppose I'm looking at a term, expanding at order n. So and then I have, each vertex will be denoted symbolically with a cross because it's associated to a position. Okay, you have 4 fields, and each field is represented by this half line. Okay, so you have n of these vertices. Well, the fields are not exactly the same position, but for the purpose of this argument, I will represent them as if they had exactly the same position. So x1, x2, and so on. Okay, I have these n potentials that I want to start contracting all the way. And so there is, for instance, suppose I contract them in this way. I have this kind of thing. That have one, okay, let me make the drawing. This ring of, so each of these things is one of these vertices. You see, it has 4 outgoing lines, so there are 4 fields, and I've chosen to connect them this way. Okay, so here maybe I have x1, x2, x3, x4, and so on. And now in principle, what I have to do is to compute for every of these line I put a propagator g, x1 minus x2 and so on, and then I have to sum over all the positions. Okay. Now, what happens, of course, there is translation invariance, so one position will just give volume, and then there is a sum over all the relative positions. So it will give volume times the sum over all the rest, so x2 up to xn, where the x1 has been fixed to the origin of the same. Now, maybe one could try to compute exactly the sums, but in general it's hard. So what one may try to do is to give bounds on this thing by bounding the propagators. Of course, in a diagram like this, it will be hopeless to give exactly the value. Okay, so the best one can do is when one does so. When you like take absolute values for the propagators, because it's hard to do anything else, and you pass to Fourier space. So here I'm skipping computation because I just want to point out that things go back. I don't want to do the computation precisely. What you get is the following, something like the integral on the momenta. Okay, you have the propagator, the Fourier transform of the propagator, which is 1 over mu. This is taken n times, where n is the number of these shapes, times a certain f of p, also n times. So 1 over mu just comes from these lines here. Each of these lines has a single propagator, so it is a g of x2 minus x3. So in Fourier space gives you 1 over mu. So I'm just using the whole thing. There is a convolution, so this is what you get, why you get a product. And f of p is just a Fourier transform of this part of the diagram. Okay, so believe me,
the points are n, maybe it's n over 2, but depends.
Yeah, suppose I have 2n of, yeah, I think I have 2n, maybe I have 2n vertices.
So it's 1 over mu all to the n.
Not just a 1. Yeah. So you have n of these single lines that gives you in Fourier space 1 over mu. Mu is the same thing that appears in Prof times another thing computed at p power n, which comes from this n kind of bubbles. Well, unless you have very nice cancellations, but that you don't see certainly taking absolute values, well, this maybe at p equals 0, you may hope it does not diverge. Maybe it behaves like a constant at p equals 0. But this one at p equals 0 diverges like 1 over p. So here you see something that clearly does not converge. Okay? So the point is that if you just, either you are able to compute exactly the diagrams and then see cancellations and things, but otherwise, if you just want to prove diagrams don't diverge too much, then by just doing simple bounds, you run into problems immediately because of the singularities of the probability. So as you see, as soon as p is n is larger than 2, you see a problem. Okay, so this was to point out that if you don't do something smarter, then single terms of the series have a problem as lambda goes to infinity. Of course, as long as L, the size of the box is finite, and here there are finite sums, there is no issue. But the issue is when the sum become integrals and then you have the really singularities. Okay, is this point clear? Okay, so since it's hopeless to try to look for cancellations diagram by diagram, this is not the way things work. I mean, this is not the way things can be really analyzed. So the idea is to try to see where really the problems come from. So, like the problem here comes from momenta close to the singularity. So the idea is to do what is called a multi-scale expansion of the problem, which is similar to what is done in 5-4 theories, and it's not proper to fermions. So the idea is to sort of to try to isolate the singularities by this so-called multi-scale decomposition. So let's see what happens. So the idea is it's following the original idea of Wilson on the normalization group. It's to start integrating out the degrees of freedom which are on large momenta, so they don't give problems, and then getting closer and closer to small momenta and see how to cure the singularity. So this sounds very vague if you have not seen it before.
Yeah, so this, maybe I can make a comment. Yeah. This is actually, these are infrared divergences, and they're not renormalizable. Right? I mean,
no, they can be taken out by, it's a field strength renormalization. It's a field strength renormalization.
Yeah, but they're not renormalized. I mean, this is non-Gaussian fixed point we're going to be getting at, right?
Yeah, but this particular one you can cure with just like a 5/4 with a gradient 5/4 gradient.
That's right.
So you can cure that by just you can cancel that bubble.
It's a little similar to the dipole.
Yeah, and it's just a renormalization of it.
Okay, maybe. Anyway, the only thing I was saying is actually just for the rough path people that this is a situation where we're trying to do it with just finitely many logarithmic divergences. It may not be so simple, but maybe it is. But
no, but I think it's renormalizable.
Yeah. My comment
is
would
not
be
super renormalizable.
It's not super renormalizable.
But it's renormalizable.
Yeah.
Ah, okay.
That's it.
Yes.
We don't have a finite number of the divergence.
Let's go on.
I think the real point about what David was trying to say is that you have to look at the 4-point function. And in the 4-point function, you'll see a log.
Yeah.
Which you cannot cure. This one you can cure.
Yeah, okay. There are other diagrams that give problems which are like
Exactly.
sausages.
Yeah.
But I just wanted to give the
Yeah.
simpler
Well,
case.
that you cure with a simple counter term or just adding it into. You see the same thing in a quartic theory, right? With gradient phi squared or gradient phi to the fourth. You would have lines you could form like that. You get that bubble. That's right.
Yeah, I didn't- yeah. Alright, so the idea is to restart from the propagator of the free theory. So let's say G, well, it could be plus or minus G omega. Let's say G plus of X, which let me recall is given by dt 2 pi squared. This is also something that appears also, I think, in works by, I mean, approach by Massimiliano and co-workers. I mean, the paradox expansion, I think, will do things that are similar to what I will do. Okay, all right. So the point is to, well, you have your singularity as 0. You have your sort of indicator function that is such that momenta are just integrated in a certain set around 0. And then the idea is to break this integration, this integral into concentric, well, they don't do concentric rings around the singularity that whose size actually decreases geometrically, so it doesn't also be the case, but so this is something of scale, so maybe 1, this is a half or a quarter, and so on, to decompose the integral on rings which are closer and closer to the singularity. Okay, so the way to do that is to just define, to write chi plus of p as, well, do a chi plus of something as chi plus of something minus chi minus 1 of something that I will define in a second, plus, and then you re-add the same thing and then subtract. I'm just making precise this thing of decomposing on smaller and smaller rings. Okay, what is chi h of p? H is a negative integer. It's just it's just chi of 2 to the h, 2 to the minus h. Okay. So this thing here, well, this is concentrated in the whole disk. This thing here is concentrated on the first ring. This other is concentrated on the second, and so on. So each of them is smooth, is infinity, but each, maybe I give them a name, yes, this one I call, this difference I call F0 of, this is F1, F5 minus 1, and so on. So FH is concentrated on FP, is on P, such that the momentum of P is of the order 2 to the h. Okay. And it's, so I'm just breaking the integral as a sum of integrals like this. Well, the 2 is the choice. All right, so at some point the procedure stops. The reason is that as long as you're in finite volume, you actually have written integrals, but in reality they are sums. And at some point, if you go very close to 0, there is no more point. Because the closest point to 0, if you remember, so so for finite volume, for finite L, the momenta were of the form pi, I1 equal 1 and 2, 2 pi over L times an integer plus 1/2, and I from 0 to L minus 1. So the smallest momentum is of order 1 over L. So at some point, this you have nothing left. So this procedure stops at a scale of order log L. At the end, you reach a final scale HL, and so you just a telescopic adding and subtracting, and at some point you stop when HL is of order along base 2 of it, because then there is nothing more. Okay, so but this is just an minus. Yes, thanks. Yes, and H are negative. Okay, so just an identity. I split the original thing as a sum of things, and then I stop when there is nothing more to be summed. Okay. So corresponding, I've written G plus of X as a sum over H. Maybe from this H tells us 0 of G plus H of X, where notation should be clear. It's just the thing with this replaced by FH, and then plus the last one, which is denoted. It just decomposed it. Now,
sorry.
Yeah.
I mean, it's minus log L, no?
Yeah, I did.
Okay.
There was a yes.
Okay.
Some pointed out, yes, sorry.
Yeah.
It's negative. It's negative. All right, so now each one of these, the whole propagator we saw earlier, it decays like 1 over the distance. Now, each one of these will decay faster. Well, so remark. For every fixed this G on scale H decay faster than 1 over the distance, simply because in the integral there is no more the singularity. The singularity 0 is cancelled by the fact that this, because this FH are 0 around 0. So you are taking the Fourier transform of a perfectly C infinity function of the torus. So, but of course, I mean, there is no miracle. As soon as when H gets more and more negative, you are getting closer and closer to the singularity, so the problem reappears. Okay? So it's easy to get estimates on how they decay, how these things decay at infinity. So let me give it as a lemma, position, whatever. That I will not prove, but it's quite easy to prove. Then, so what you have is that the propagator on scale H behaves like smaller equal than a constant times 2 to the H. 2 to the H would be just 1 over the distance, because the momenta are concentrated near 2 to the H, so the X is ordered to the minus H, and then this is like a 1 over the distance, and then times e to the minus. Okay, so what is this thing saying? This is saying that the propagator on scale H behaves like 2 to the H, but then when you go on distances which are much larger than 2 to the H, 2 to the minus H, then you get something small. Okay, so what is the point? So if you were taking a Fourier transform of a function which were analytic, then you would have something that would decay exponentially fast with X. Now your functions now f over n over mu is infinity, but it's not analytic because it's 0 outside the finite domain. So you cannot hope to get something decaying exponentially in infinities. But you can take it smooth enough. You can choose this chi smooth enough so that this decay is this way. Okay, so
it's not so important that you have this e to the minus square root. You could do with some inverse power or so.
Well, in some technically, at some place it's convenient to have this. Okay. You have to really choose the chi in some algebraic family class so that it's very smooth. But at the level of this course, it doesn't matter. When you really enter some details, it does. Okay, so I hope it's clear. So this thing is just, you should read it as 1 over the distance where x is of order 2 to the minus 8. And this thing here tells you that when you take distances which are much larger than that, you start seeing the C-infinity, actually more character of f, which makes the very much. Okay, so but it's okay. It's a question of estimating integral sum. It's not something very deep.
So does the C-infinity part come from where the thing cuts off?
Again?
The C-infinity part of this thing here, when you get the analytic bit,
Yeah.
is this for large momentum?
Is this what?
Is this for large momentum? Is this in that region?
No. The momenta here anyway are between pi and pi, so large momentum doesn't exist here. But what I'm saying is that the point is that so you are in space. So suppose I'm just taking the modulus of p. I'm integrating something like this, centered around 2 to the h. What I'm saying is that, well, that this prefactor comes from the fact that the contribution is from p of this order, and then the fact that you get this precise way of decay depends on how smooth you have chosen this cutoff. If you really chose something rigid, you would have something really bad. But and if somehow this were analytic, which is not, you would get exponential.
No, but square root has no meaning. I mean, you can have any power less than 1.
Yeah.
That's,
You cannot have 1.
yeah, you cannot have 1.
Yeah, but even that is just because you're insisting to have compactly supported cutoff function. You could even have an exponential. I mean, it's not very important.
Yeah, at the level of this course, just think of having this thing and then have something very small if this quantity is large. The square root doesn't really, it's not very important. It was just to write down something definite. It confuses more than helps. Okay, so what else? All right, so maybe the thing I can do is try to sort of set the stage for the multi-scale expansion, because for the moment I just expanded the propagator, and then okay, so what is the multi-scale? Of the generating function or of the partition function. Well, the thing is that in Z, remember you have an integral of something depending on psi. And the point is that, well, the reason I decompose the propagator is that I want to write every Gaussian variable as a sum, again as a sum of Gaussian variables on scale h. From whatever HL to 0 to 1. And, all of them are diagonally with respect to the index h and have the propagator g plus g omega h. Okay, up to now it's an idea. And now the idea of the Wilson normalization group is to start integrating out first the scale 0, then the scale -1, then the scale -2, and to try to fix the problem coming from divergences scale by scale, not once they have already exploded. Right, so what is the idea? So the idea is we have like Z, which is maybe divided by, okay, Okay, and then, so, okay, then you write it as psi 0 and then the idea is to start integrating out psi 0 HL okay, so here I'm still at the level of identities. Okay, so the idea is you start integrating the scale which is on largest momenta, so farther away from singularities. Once you have done that, the second expectation will come in and so on. So what is the general structure? The general structure is that you start from a certain potential, which may be most purely quartic. Once you've integrated out the first scale, you will have a new potential. So the point is to define, suppose this V, I call it also V, I put an index 0, so it's just the original one, the quartic potential, for instance. Then once you have once you have integrated out the first scale, by definition, what you are left with is the new potential V minus 1. Okay? So this is the definition. So once I've done my integration, I call what is left as the exponential of the new potential.
Yeah, this E0 is not the original E0.
Yeah.
You called E0 two different things.
Maybe
okay,
maybe
sorry,
it's
I'm sorry.
maybe wipe out the first 0.
Also, I'm forgetting 1 0 from
Yeah,
one.
but that's not the same as.
No.
What did they call this? Sorry. No,
Take that away and that one away, right.
Maybe
Okay,
this is.
yeah.
Yeah, I'm sorry. E is the, yeah, sorry. You understand. Okay.
Don't put anything.
Not put anything. Good suggestion.
Yes.
It will be on the video. Anyway, all right. So, okay, so this is the definition of V1, and then down here it is area 0. And then this one I expand as I did in the equivalent expansion before. So this one will be given by V1 V minus 1 of psi. When I write psi minus equals something, it means the sum over the psi's before that scale. Is again the sum
So why did you cancel the alpha? Maybe it's a bit
the what?
The alpha has.
Yeah, because I forget. All right. So now this expectation, I write this potential. I write as a sum of accumulants. And now, I mean, it's sort of in the same situation as before, but actually, I'm in a better situation because all the problems I pointed out of this diagram diverging, it does not appear anymore because the propagator on the scale 0 does not decay in its momentum like 1 over p. Actually, so I mean, that does not diverge with 1 over p is perfectly regular at p equals 0. So the point is that scale by scale, you don't have strictly the divergences, but eventually they will appear because now we will start integrating smaller and smaller scales. So if you don't do anything, the same problem will reappear. But at least you have the chance to do something step by step instead of having something directly divergent. All right. So the idea was to, but it's I think hopeless to explain how the hierarchical structure emerging from this multi-scale. Maybe I can do the first, second step and try to convince you of what kind of hierarchical structure comes out. Okay, so let's see what happens here. So here I have a sum over n. So there is a way to graphically represent this kind of expansion in the following way. the term with a certain index n is represented as a tree with n leaves. This is the tree representation, tree expansion, at least in this form introduced by Gallavotte and Nicolò. I don't know that all this. At least in this version, they're called Gallavotte and Nicolò trees. Okay, so in this expansion, what happens? You should see the following. This is on the horizontal axis there will be the momentum scale, and here will be the scale 0 because that is the scale on which I'm doing the integration. I'm doing the expansion. This is the scale, if you want, scale by convention 1 where nothing has happened yet. So you should think that when you have, like here I have n equals 3, I have 3 of this potential. So here at the leaves of this tree, you have the fields, you have the V. V at position x1, V at position x2, C of position x3, and so on. And then this thing means that when I'm moving to scale h0, I'm taking this truncated expectation. Okay. And then I will put the root of this tree at the next scale, -1, because then at the next scale I will use this tree to construct another tree of larger depth. So, okay. But that's not all, because when you see this expectation, so remember each V is a product of 4 fields, phi, psi, but each of them can be either of scale 0 or lower scales. So, for instance, this is a product of psi, psi plus, psi minus, but each of them is written as psi0 plus all the rest. So when I compute, okay, each of them you will decompose like that. So when you expand all these products, you will get terms maybe with just psi0s, terms with just psi of lower scales, and terms with all of them. Okay? And the expectation here will act only on the terms of scale 0. So there are, according to which term you choose, you have various contribution in your expansion. So I hope this one is clear. So maybe later give an example. Suppose you have, maybe I just take certainly just take n equal 2, and maybe I pretend, well, the expansion is a bit heavy, admittedly. So I've never seen a very elegant way of explaining this. Okay, I think the example will be less clear than okay, we've never entered the backward. So okay, let me go back to here. So let me ask if this is clear. So I have a product, I have all these are monomials, but each variable in the monomial has been split on the variable on scale 0 and the variable on scale smaller or equal than 1. Now when I expand the monomial, I get many terms. So the monomial becomes a polynomial. And now when I take the expectation acts only on the things with index 0, not the index 1. But I have many terms because is this okay? Yeah. Okay, so there is a way to put labels on the trees. So maybe I will just do the same one. Easier to work with. Okay, I will write down the formula and then comment on it. And, okay. What will be this v minus 1 of c more equal than minus 1? How will be given? It will be a sum over n. It's the same as here. There will be an alpha over n factorial, 2 over n factorial. Then there will be a sum over these trees, like this, which have a root at scale minus 1, have n leaves. Then there is a sum of something which I will explain in a second. So tau is the name of the tree. There will be a certain p tau, which I will explain. And then will get this is the first part of the formula. Let me first explain this first part, and then the second part will be hopefully clear. In the second part, this is not all. So, what am I doing here? So, to each endpoint you have a potential. So a potential is a collection of fields. So let me call P, so the endpoint will be called V1 up to Vn. And associated with that you have a collection of 4 fields. Let me call it PV1 will be the indices of the 4 fields appearing there. Okay, so it's a product of 4 fields, and they have the indices in position, in omegas, in everything. They have to be taken as ordered set because it matters in which order they come and so on. And then there is the last one, we have the PV end. Okay? And so that denotes the indices of the fields which appear in the leaf end. Okay? And then in this first term, I'm assuming that in the expansion I've taken only terms of with phi0. Okay? So once I've done the integration here, this is, let me call it V0, this first term, there will be nothing left. So PV0 will denote the fields which are still left there. So the fields of scale smaller or equal than -1. If I've taken terms which only if in this expansion I take only terms of with index 0, then nothing is left there. So here. So this part of the formula just means I'm taking all the contribution from all the contribution when all the C's are replaced by C0, and then there will be other things. So this is a number. I mean, everything is there is no fields anymore. Everything is average. This will give a number, okay? And this will contribute as a generative function. When I continue in my multiscale expansion, this will.
No, it's not a number. There are still lots of Grassmann variables around.
No.
Yes, absolutely.
No, I've not finished the. I'm not finished the formula.
Oh, I see. This is
right. Okay. Sorry. So this is the part. This is the contribution from all the graphs where the C minus equal small equal than -1 doesn't appear. This make a number. They will not. They go out of any other integration. You understand?
So the sum is on PV0 or?
Yeah, sorry. It's the sum of. So this. Okay, I didn't introduce the full notation, but the way to read it is called the contribution for all the terms in the expansion where you just pick the phi0s. Then, of course, there is much left, which is. You still sum over the trees, but then you allow your PV0 to be non-integrable. In this case, you have. It means that from each of these things that have 4 fields, some of them will be taken with index 0, some of them not, but at least one will be taken to be index non-zero. And okay, so here there are some notations. I don't see how to give them better. Will you need these notations that I was about to introduce, or otherwise it makes no sense to mean -1?
Yes, but I don't know, maybe it's late.
It's
I
late.
can also.
Yeah, sorry, I sort of underestimated the time needed to write down, but.
Maybe you should keep away the secret.
Hmm?
Maybe you should keep away the secret.
So I should write down that.
No, but I mean, I guess the point will be that some terms will survive when you rescale, and other terms will become smaller when you rescale.
So the thing I wanted to do.
Finitely many terms will be important.
Yeah, but I'm still far from that actually. I wanted first to explain how to represent the expansion at scale h as a sum of trees of scale h, and then to analyze which trees pose any problem, which do not. And then, as you say, only a finite number of problems have to be cured, but sort of still far away from that. This was just to sort of set the stage for this multi-scale expansion, but as you see already, the first step was.
But you can work this iteratively.
Yeah, that's
That's
what.
what it does.
Okay, the idea, the other thing was to write down directly the formula for scale h, and I was trying to give it at scale -1, and then to convince you that scale -2 that a certain structure emerges, and then to write down the formula at scale h, but it took longer than that. So maybe some of you can start from there, but let me just write down the formula for scale 1, for scale -1. So what you have here is you have to sum. You have to sum over n. For each n, you have a collection of 4 fields. And now this index means that not all of them have been taken with index 0. So what you get is you have a certain expectation at scale 0, but from each of the leaves, you don't get all the fields which were there, the 4 fields. Some of them remain. That just means that from the leaf 1, a certain subset of the fields, say 2 of them, were of scale smaller equal than -1, so they don't appear in this expectation. And then from the, I don't know, from the leaf number n, not all of them were integrated, a few of them. So the Q denotes which field from leaf n where you pick the index smaller equal than 1. Okay. These are integrated, and then what is left, all the fields which are left are there. So then you get the product of the fields on scale smaller equal than 1, with those which were not integrated from leaf 1, blah blah blah. And just to say something, when I write psi with the subindex q, it means the product of the fields in the index set q. Okay? And then there is a certain signature of the permutation needed to put things in the. Okay, maybe the details are not so important at this stage, but it just means that in the first thing, I'm collecting all the terms where from all the potential I've chosen the index 0, so everything is integrated out. And from the second terms, a few fields are still surviving, and then they will enter the next integration. They will enter the definition of V2 and so on.
So does tau identify what the Q's are? The tree?
The tree, yes. So in the general, so here there is not much to be chosen. So once you've given the leaves, you have the, there are 4 fields and so on, and then I just have to give you which one have survived. But in general, when you have a tree with depth h, to each you have the field labels on the leaves, and then at each branching point you will say which one have been integrated out and not. So the tree contains all this labels.
Okay. And it's going to get arbitrarily long.
Yeah.
So what is the point of having V around? I don't understand. Why you cannot just write P1, Pn? There is a V. No, the small v. I don't see what the information carries.
No, it tells you. It tells you, for instance, this one is telling you. So PV1 is the collection of 4 indices, which is so the 4
fields.
fields.
You cannot call it P1.
P1 rather than PV1. I think that's a possibility.
So it's a notational.
No, V
but I
is
thought
not
my notation was
meaning.
too simple. No, sorry.
No,
No,
I'm
but
asking if V
no.
contains meaning or not.
Well, it does not as long as the trees have depth 1. But once you have a tree of depth like this, then for each vertex you want to give a name to its children. I mean, 1n is just for the endpoints. Once you have a tree of an arbitrary list there. I want to say for each here, I want to say how many fields are integrated that we are seeing here, how many are surviving one after integrating, so on. So here it is not sufficient to give an it's 1, 2 because for each branching point V, I will have a certain number of children, maybe 1 to Vs. So, but I agree, as long as
No, okay, just
on scale -1, it doesn't give anything.
because you are in the root now. I don't know, or something. You are in the root, so
Here, but here, I mean, there is just the leaves and this point. There is nothing more. But once the tree is longer, you cannot just put ones ends because there are. Once you repeat, so at the first scale you have a 1 over n factorial, and then now you repeat. So each of the by v minus 1 have another n, so on. Okay, so but we'll say. So the plan would be to, okay, so I don't want to speak for Alessandro, but my plan would have been to give you the general structure and then tell you how to identify the trees which have problems, like those corresponding to these bubbles or the sausages, and then proceed.
I guess the kind of technique you're presenting is geared to fermions. If you have bosons, you will probably run into difficulties because of the large field
Yes.
problems and so on.
Yeah, something I didn't, that's perfectly correct. So, the point is that, I don't know whether this answers exactly your question, but the point is that even if when you cure the problem of the divergence of these graphs, you still have to resum everything. And there, the determinantal structure helps.
Yes.
And we use these formulas by Bridges, Federbush, I forgot the
Everybody,
yeah. Anyway, so so it's essential that in these graphs you have signs.
Yeah.
Yeah. So the answer is yes. It is essential that we have.
Yeah, so certain part of multi-scale fermion expansions is actually convergent, and you can write
Yes,
out this detailed formula for it, which is beautiful. And with the Bose case, you don't try to do that because the expansion is
Yeah, there you cannot hope because
That depends.
no. Here in the end, it's converging. Except you don't see it. To see it, you have to look at the renormalized expansion.
you have cut off this conversion. So long as you have cut off the sunlight, because determined analytic.
Yeah.
Okay, thank you very much.